Well, the next question we want to consider is equilibrium versus stability. And you may ask, is this an equilibrium problem or a stability problem? Well, it depends on the question. So if there's an equilibrium problem, something is stable, it's not moving, it's obviously not moving, you may want to find out what the reaction is. In other words, you assume it's stable. However, stability problems may be something where you're asking, is it about ready to tip over? Or what force does it take for it to tip over? For example, this crane problem right here. You can see that if we loaded it up too much, it might rotate or tip over about this front and tip over this way. And if that's the case, then the driver kind of gets ejected out of his seat, and then we have kind of an accident. So in other words, this would be a stability problem when we're asking, what is the force at which it becomes unstable? Or when does it tip over? When that happens, you should look for a condition where one of the forces or one of the reactions goes to zero. For example, here, if it tips over here, then A is going to go to zero. And we're going to solve this in just a second. For wheelbarrow types of problems, we may find out at what point does the center of gravity go over the tipping point. And then we'll talk about that in just a few seconds. So let's solve this crane problem real quickly. And what happens here, or what's going on, is the crane is about to lift something up. The crane and driver weigh 2,500 pounds. There's the center of gravity right there. And we want to find out the largest weight of the drum so that it is not unstable. If it becomes unstable, what would happen? It would be tipping over the front, and then A goes to zero. So let's draw a free body diagram. It's got a center of gravity, and mg is the weight. There's going to be a reaction at A and a reaction at B, and then there's a weight coming down here. All right, let's do our equations. So in almost all of these equations, what we're going to do is recognize that at tip, it will rotate at about some point. In this case, it rotates at B, and A goes to zero. So if you'll just write that little love note to me on your problems when you're doing the exams and that sort of thing, that will help us communicate. That'll tell me that you know what is actually happening when this thing becomes an unstable situation. Most of the time when we solve tip over problems, it is one equation. It'll be a moment equation. It is most logical that we'll do the moment equation about the point of rotation. So let's sum the moments about the point of rotation. In this case, it is point B. What we got? We have this mg times this lever arm. So this is mg coming here. The lever arm is here, which should be 8.4. mg here is 2,500 pounds. So I'll say that that is 2,500 times 8.4 plus 1.4. That's the total lever arm from the center of gravity to the point of rotation. The only other thing causing rotation would be this weight out here, and this is going to be the lever arm right there. This will be the lever arm right here. How do I find that? Well, I'm going to have this point here, so this is going to be 10, oh I beg your pardon, it's going to be 15 cos 30. That's the total distance, this being 12 and 13. Then it's going to be subtracted 8.4. So let's go ahead and put that in there. So and that'll be trying to rotate in the clockwise condition, which is negative. So I'll say minus weight times 15 cos 30 plus 8.4. Whoops, I beg your pardon. That is minus 8.4. And that gives me that distance right there. And that's equal to 0, so I can easily solve this for the weight. Is it going to be equal to 5,337 pounds. And that is the maximum load you could lift without the whole thing tipping over. Alright, well here's a little example of a gentleman who is trying to play a foolish game here, but he is going to walk this way until this whole thing becomes a dynamics problem. So part of understanding statics is trying to figure out what is stable, what is not stable, what's going to happen. Maybe you can guess that the farther out he goes, the more dangerous it becomes, and pretty soon it's going to become unstable. So go ahead and pause the video and work out the solution for this, and then we'll start it up in just a few seconds. Okay, well, here's the solution. We recognize that the man weighs 200 pounds, and here he is at some distance x. At rotation, or at unstable, at tip, it's going to rotate, this whole thing is going to rotate at B, and whatever the normal force at A is going to go to 0. In other words, everything's going to go this way. That's what happens. Alright, so let's work out some other things here. It says that the wooden plank weighs 10 pounds per foot. Alright, and the whole plank is 16 feet long. So that means that the plank weighs 160 pounds, and then you can work out the center of gravity of the plank at 8 feet, and you can see that that is 3 feet from the point of rotation. That's where the center of gravity is. It says that the bricks weigh 75 pounds. The bricks are a triangle load, so what is that? It says that it is 2 feet in this direction. So the center of gravity of the bricks will be 2/3 of 2/3 feet, if you will, from this side, or 4/3 feet from that side. So because this is 9 feet here, minus 2, that's 7, minus another 2/3, that's going to be the total lever arm here, which is 9 minus 2 2/3. Anyway, then all we have to do is sum the moments about point B and see what we get. So let me just move that up here. Sum the moments about B. And here's our picture. I have 75 pounds times this lever arm going in this direction, 160 pounds times this lever arm also going in that direction. That's balanced by 200 times x going in that direction, and you can solve for x is 4.775. Well, the last thing to consider here is the wheelbarrow problem, and we'll be doing more with wheelbarrow types things and stability things as we go forward, but I just want to mention it here. And what happens is that if you lift this wheelbarrow up, it's got a block here. It rotates about that point, but what happens is as this goes this way, at some point in time, you need to hold it back instead of push it this way. And the point at which it becomes unstable is when the center of gravity goes over the point of rotation. So if you lift this up a little bit more, when the center of gravity goes over the point of rotation, that's when it becomes unstable, and we'll try to rotate that way, or begin to rotate that way. So it goes unstable when CG goes over the point of rotation. So if we were to find this angle, alpha, or this angle right here, I beg your pardon, this angle right here. If we can find this angle right here, where this is now a right triangle right there, or right angle right there, and this internal angle right there, that would give us an angle alpha, and then as it goes over this way, that happens. So all those dimensions are given, 0.3, 0.5, that internal angle alpha. If I just rotate it a little bit more, that angle alpha, how much I have to move it before it becomes unstable. I guess I started with an angle of 25 degrees, so I add that to that, and the total angle would be up 50 degrees from there.